Recording. So the majority of these topics will be on your midterm this Wednesday. That's why we're doing this virtual SI session for everyone. So let's go ahead and start with oxidation numbers. These are some of the rules of oxidation numbers that you have to basically memorize. The first one is that all pure elements and diatomic gases have an oxidation number of 0. An example of this is in O2 gas, the oxidation number of oxygen is 0. Second rule is that any monatomic ion has an oxidation number equal to its charge. An example of this is in tin. The oxidation number will just match whatever charge it has. So in this case, +4. Rules 3, 4, 5, 6, and 7 are ones that you should memorize. It is that oxygen has an oxidation number of -2, except in peroxide, in which oxygen has an oxidation number of -1. So that's an exception that you need to memorize. Fourth rule is that hydrogen always has an oxidation number of +1, except in hydride, it has an oxidation number of -1. Number 5 is fluorine will always have an oxidation number of -1. And all 1A elements have a charge of +1, and all 2A elements have a charge of +2. So keeping these oxidation numbers in mind, go ahead and calculate the oxidation numbers for each element in the compound.
So right here we have NBF5. So we know that the overall charge is in the upper right-hand corner, which is which all the oxidation numbers have to equal to. So in this case, we don't know the charge of NB5, but we do know that fluorine is -1. So and we know that the compound's overall charge is 0 based off of whatever is in the upper right-hand corner. So to do this, we have to set up the equation. NB plus 5, which is 5 fluorines, times -1, which is the value of each fluorine, is equal to 0. In doing algebra, we find that NB is equal to +5. Now then, in order to make sure that NB plus 5 is NB plus 5, you just check your work. So you put back +5, and you just resolve it. For NB, or you resolve it, you put in back +5 for NB, you resolve it, and yeah, it checks out for 0.
Yeah, basically you want to make sure that when you add up all the charges for each element in the compound, it should all equal to the compound's overall charge. So in this case, if NB is +5, and we have 5 fluorines, +5 plus -5 should equal 0, which is the compound's overall charge.
All right.
Wait, let's try another one. We have a compound whose overall charge is not equal to 0. So this should be a little more challenging in terms of algebra. We do know that oxygen has a charge of -2 for its oxidation number. This should be memorized. And we also know that the compound's overall charge is +2. So knowing these two pieces of information, we can set up our equation. And if we set up our equation, we can solve for uranium's oxidation number. And as always, check your work.
Yep. So some oxidizing reducing agents. So you already know about the numbers. Now let's see how we fare with reactions. So there are two main reactions to redox, which is a reduction reaction and an oxidation reaction. So on the left, when the chemical gets oxidized, it has 3 properties. It loses electrons, it becomes the reducing agent in your reaction, and it becomes more positive. While on the reduction side, where a chemical reaction is having a reduction reaction, it gains electrons, it becomes the oxidizing agent, and also it becomes more negative, because we know that electrons are negatively charged, so the more you gain, the more negative you become. And?
Wait, a helpful way to remember this is Leo Ger. Basically, LEO stands for lose electrons oxidized, and GER stands for gain electrons reduced.
Oh, so why don't we try out? A problem where we need to know which one's the oxidizing agent and which one's the reducing agent for the following reaction. So it's chromium 1 plus tin 4 produces chromium 3 plus tin 2. So based off of
Okay, so the strategy here is to look at the charges. Chromium's charge went from +1 to +3. This means that chromium became more positive, therefore it lost electrons, and therefore it was oxidized. So chromium must be the reducing agent. We can use the same strategy for tin. If we look at tin, it went from +4 to +2. Tin became more negative, so it must have gained electrons. And if you gain electrons, you become reduced. And if you become reduced, you're an oxidizing agent.
So, as you know, that some of the stuff, not all redox reactions look like the one before. So, in order to solve them, we can't really use like the balancing chemical reactions like how we're really used to. So instead, we use it through solve it through half reactions, which is the steps all labeled here below, right? Which is all the steps here. So if we follow these steps, we can balance out the following redox reaction. So we have HCOH plus MnO4 minus produces CO2 plus Mn2 plus. So how do we do this, Claire?
Alrighty, so the first step is to write out two half reactions, and you write them like so. HCOH turns into carbon dioxide, and MnO4 minus turns into Mn+2. After that, you're going to balance everything except hydrogen, oxygen, and charges. So for the first half reaction, we only need to balance carbons, and it looks like they're already balanced because we have one carbon on each side. For our second half reaction, we only need to balance the Mn, and it looks like it's already balanced because there's one Mn on each side. After that, we need to balance the oxygens with water. For our first half reaction, it looks like we don't need to add any water because there are two oxygens on the reactant side and two oxygens on the product side. However, for our second half reaction, it looks like there's 4 oxygens on the reactant side. So how many waters should we add, and to which side?
So since permanganate, which is the one on the left, has 4 oxygens, and manganese only has 2 plus, you need to add in 4 water molecules to balance out the oxygen, because we know that for every 1 water molecule has 1 oxygen. So 4 times 1 is 4. So that's how we balance that one out.
Exactly. After that, balance hydrogens with H+. So for our first half reaction, it looks like there's 2 hydrogens on the left side, but 0 hydrogens on the second side. So therefore, we're going to add 2 H+ onto the right side. And then for our second half reaction, we added, it looks like there's 8 hydrogens on the product side. So we're going to need to add 8 H+ on the reactant side in order to balance it out.
Yeah.
Finally, we're going to need to balance the charges by adding electrons to the more positive side. So to do this, it's a good idea to keep track of what the overall charge is on the left side and the right side for your half reactions. So for our first one, we have a neutrally charged molecule. And on the other side, we have 2 H+. This means that the overall charge is going to be +2 for the product side. And then same thing for our second half reaction. We have 8 positively charged 8+ or H+, and 1 negatively charged MnO4 ion. So this makes our overall charge +7 for the left side. And then we have +2 charge excuse me, on the other side. So how many electrons should we add, and to which side should we add them to?
So, of course, we always add electrons to the more positive side. So for the first half reaction, the product went from 0 to +2 in overall charge. So we add 2 electrons on our product side to balance it out. And for the second half reaction, we went from a +7 to +2 in overall charges. So we now add 5 electrons on our reactant side, so that way we can go from, that way we balance it out. We balance out the charge itself. So after we do that, so now that we have balanced out the overall charges, now we have to cancel out electrons. In order to do this, we have to multiply the 2 reactions by the least common multiple. In this case, it's 10, because 5 times 2 is 10. So we need 10 electrons in total for both the reactant side, for the first half reaction and the second half reaction. So in this case, we multiply the entire reaction by 5, the first one, by 5 to get 10 electrons, and then we multiply the entire reaction by 2 to get 10 electrons as well. So anytime when you do balancing electrons like this is where people make a mistake. They only multiply to the electron and they don't multiply to the rest of the reaction. So you have to make sure that you bracket the entire reaction and then multiply it by 5. Oh, multiply it by the multiple that you need to balance out electrons. And here, and after that, after we balance out all the electrons, we now just combine the 2 half reactions together. And after we combine the 2 half reactions together, we just do is simplify it furthermore just to make it look more nice and clean. So in the box below is the overall simplified balanced redox reaction.
Yeah, so when you simplify the equation, you're just basically going to be looking for what else can I cancel out. So in this case, we have 16 hydrogens on the left side and 10 hydrogens on the right side. To simplify it, we can cancel out these extra 10 hydrogens so that we have a net of only 6 hydrogens on the left side and 0 hydrogens on the right side.
Right. So now that we're done with redox, why don't we go over titration? So the whole point, the whole reason behind titration is just to conduct an acid-base reaction where base is used to neutralize all acids or most of the acids in a given unknown solution. So, problem. So an ascorbic acid solution was made by dissolving a vitamin C pill in water. The solution was titrated to end point with 14.5 milliliters of 0.467 molar NaOH solution. So pretty much we're trying to figure out how many milligrams of ascorbic acid, which is a monoprotic acid, was in the pill.
Alrighty, so there are steps that we can, or that we recommend we take. First is to draw a picture so that you can help understand the situation better. We have a known amount of NaOH, but we're trying to find an unknown amount of ascorbic acid. So we're adding 14.5 ml into a mystery molarity ascorbic acid solution. Next, write out any useful formulas or chemical equations that you remember. So in this case, we know molarity is always equal to moles over liters. And then finally, we can start our calculations. We know that the equivalence point means that all the moles of acid have been neutralized or eaten up with base. Therefore, if we know the moles of base, we also know how many moles of acid there are, based on if the acid given to us is monoproduct, diproduct, triproduct, etc.
It's like 1, 2, 3 acids. And note that equivalence point is the same thing as end point. It's just when all the acids has been neutralized by base.
Yes. So monoproduct acid means that only 1 mole of strong base for every 1 mole of acid is required to neutralize it. And that's what we have here. We converted the molarity, or because we're given the volume of NaOH and the molarity of NaOH, we can plug these into our molarity equation to calculate the moles of NaOH. And if we know the moles of NaOH and we know the type of acid it is, we can convert it into moles of acid. So in this case, since it is a monoproduct acid, we will just need a 1-to-1 mole ratio. So therefore, the moles of ascorbic acid is going to be the same amount as the moles of NaOH. So if you know this, then you can skip it. I'm just kind of showing it so that you can follow the calculations. So finally, we convert the moles of acid into whatever the problem wants us to find. We're given the molar weight to help us convert from moles to grams to milligrams. And if you do the math, you should get 1,190 milligrams of ascorbic acid. And we have some memes for the soul.
All right, so after going through all the titration and math, now we have to go into like some of the theory. In this case, we have to go over the science guys, which are a bunch of old dead people, just like Mr. Krabs over there. So some of the science guys that we have to know is about Dalton, Millikan, J.J. Thomson, Rutherford, Bohr, Einstein, and Planck. However, over here I have a matrix of which back. Sorry, technical difficulty right there. So I suggest that like this would be a great way for how to memorize or like get familiar with some of the terms of the theorists. So I made a matrix where like it's 3 columns and 3 rows. Oh, sorry, 3 columns and X rows, meaning that it can be as long as you want. So I have my theorists, the theory or equation that they made, and my understanding. So I know Dalton made the Dalton atomic theory where they cannot change an atom, where my understanding is that you can't change an atom of one element into another element. So we can't make, lead into gold. That's the point of Dalton. Rutherford's radioactivity. We found out that electrons are consistently moving and they're not stagnant, because when he shot radiation through a tin foil, he sees that instead of going straight through the foil, the light just keeps on bouncing back and forth throughout the tin foil. Einstein's photoelectric effect. He just asked like talked about light and how it interacts with matter itself. And Bohr's Bohr model, where the model stating that electrons' ability to jump between energy levels. So you know that n is equal to 1 jumps to n is equal to 5. That would be Bohr. And Heisenberg's uncertainty principle is that we don't know where the electron is exactly, but we can give an assumption of where it could be. So think of like how I think of it is like an everyday life. My everyday life, I go from home on a bus to school to go find food, back to class, go hang out, go to work, go back and hang out, go to the library, go back home. So you see that long list of like locations where I can be. Heisenberg said that like we don't know where you will exactly be at that specific point, but we know where you will be in a broad spectrum. Yeah, those are the science guys. Now let's look at energy. So there are different types of energies for this. There's different types of energies, but the main focus of here is just like knowing what are your energy parameters, like what can change with energy, and also to know the difference between emission versus absorption. So when you emit, when energy is emitted, it's when the particle jumps down energy levels, so it's releasing energy. In that case, it would be negative. And absorption is when particles jump energy levels, so they're absorbing energy. So it's like becomes positive. And here are all the parameters for each of them. Now, of course, we have the energy formulas. So the formulas for the energy, which should all be given. The constants should be given to you, but the formulas you have to memorize and know how they work. So just come on. So some energy
Wait,
calculations.
actually, so for the first energy formula, you want to be careful with the units. It says
That's
that
right.
wavelength is in nanometers, but if you plug in nanometers into this equation, you won't be able to cancel it out with c, which is the speed of light constant, which is measured in meters per seconds. If you try to use nanometers into this equation, the nanometers and meters cannot cancel out. So I'm going to change this really quickly to meters.
Where's the chat box?
And then basically wavelength, the units for it is measured in some type of distance. So it can be like centimeters, meters, nanometers, kilometers, etc. It's just that when you try to plug in wavelength into this equation, or if you solve for wavelength in this equation, know that the units are always going to be meters because we're basing it off of whatever distance our speed of light was used. So you want to be careful with that. Okay, you can continue.
Yep. All right. So some energy calculations. So the color red has around like 750 nanometers of wavelength. So I want to know how to calculate the speed of the light for the color red. So what's the speed of, so how do you calculate this, Claire, for the speed of light?
Oh, well, you can use the equation here, C equals wavelength times frequency. Low-key, this answer is like a trick question though, because all light travels at the speed of light, which is 3 times 10 to the power of 8 meters per seconds.
Yep. It's just a literal question asking for a literal answer. So if I ask for the frequency, then that's a different story. But moving on. Okay, so now then, a particle has a wavelength of around 550 nanometers. So now we have to find the energy of that one. So here we know that for a higher frequency, it has a shorter wavelength. And then for a low frequency, it's a longer wavelength. Right here. So this is like some of that conceptual aspect of like energy. So example, let's say I have like, I don't know, what's a good example of that? It's a good example of that, Claire.
Well, if you look at the electromagnetic spectrum, we know that gamma rays and X-rays are really dangerous because there's very, very high energies associated with these wavelengths. And if we're exposed to it, that could cause, bad things to happen to our cells. However, if you look at microwaves and radio waves, they're a lot lower on the frequency spectrum. This means that their wavelengths are larger and they don't carry as much energy. And because they don't carry as much energy, they can't really hurt us. So that's why it's okay to stand in front of like a radio and listen to music, but it's not okay to stand in front of an X-ray totally exposed.
We should get the lead curtain for that one. All right, so so how to calculate energy? So we know that the equation we need to know is E is equal to H times C times lambda, which I highlighted in yellow. So first off, we have the wavelength. Now we just convert it to which is 550 nanometers, but we need to convert it into meters for this problem. So in green is the amount of wavelength that we have. Now we substitute that value back into our energy equation, and we know that H and C are both constant, so we don't need to calculate anything for that one. And then we just plug in the wavelength, and that is our energy.
Yeah, so for this one, you also want to be careful with the units. Planck's constant is equivalent to that number joules times seconds. So when these units cancel out, we're left with energy, which is measured in joules. So suppose the question were to say, calculate the energy in kilojoules. If you just wrote 3.6 times 10 to the power of negative 19 joules, it would be wrong because you have to take an extra step to convert your joules into kilojoules. So please be mindful of the units for these calculations.
All right, so now, what should we call it? His name is Bohr, right? Bohr. So remember when we were talking about Bohr and his theory about how particles can like jump from one energy level to another? So here we have the energy level diagram for hydrogen, which is that same particle that Bohr was talking about. So an electron jumps from an initial energy level of n is equal to 1 to a final energy level of n is equal to 4. So what is the wavelength? So in order to solve this, first we need to find the energy between the two energy levels, being that n, which is that equation right there in purple. So RH is a constant, which is that value. We know that the n final, which stated from the stated above, is 4. So we do 1 divided by the value of the n final squared is equal to 1, which is that value right there. And then n initial is the same concept, which is 1 divided by 1 to the power 2, which is 1 over 1, which is equal to 1. Now, we just use those values and plug it back into our original equation, which is the one in the highlighted purple. So we have E is equal to negative 2.18 times 10 to the negative 18 joules. Oh, these equations will be given to us in the chat, right? The equations, I am not sure about that. I believe you have to memorize the equations, but I believe the constants will be given to you in the constants will be given to you during the test, but the equations you might have to memorize yourself. So E is equal to negative 2.18 times 10 to the negative 18 joules times the difference in the energy levels, and that's where you got 2.04375 times 10 to the 18 joules. Do you note that, wavelength, right? Okay, so the question is asking for wavelength, but now we have the energy. So, food for thought. Since this energy that we have is positive, we know that it's and we're jumping up energy levels. We know that this is an absorption. Energy is being absorbed. Like back in like a few slides ago when I was talking about emission, we were talking about emission versus absorption. We know that emission would be negative if it jumps down, and absorption would be positive if it jumps up. So since we have a positive value, we know that energy is being absorbed, which makes sense because we're jumping up from n is equal to 1 to n is equal to 4. So now we have our energy. Now that we have our energy, now that we have energy, now we can calculate the wavelength based on the energy we found. So these two energies of the one in the purple and the one over here with the lambda, they're the same. So we can manipulate this energy equation to isolate lambda, which is what we want, and we just do it to. I'm gonna just show you right here to show how to do it algebraically. We know that H and C are constants, and now we just plug in lambda. We plug in the values of HC and our energy that we found up here to get this value of 9.73. And we know that we want to have it in units of nanometers, just for the sake of this problem. Just for the consistency of having lambda in nanometers. Well, in this case, so I just multiply it by 10 times 10 to the 9 nanometers. But of course, you'll be asked of whether to have lambda in meters or nanometers or the decimeters or something like that. But it's either nanometers or meters for lambda. So that's pretty much that one. Now let's try something a little bit more complicated. All right. So an electron has a mass of that, and that jumps from initial level of n is equal to n is equal to 5. Now you need to know the speed of the electron. Now, do you know that the speed of electron is not the speed of light? So the speed of light does not equal the speed of electron unless proven. So we go back to our the previous energy equation, which is the one in purple. We solve our energy using the same process, and we have 4.578 times 10 to the negative 17 joules. Do you note that the first problem that was given, there was no limit to the sig figs, but now this one we do have a limit to the sig figs. Does that make sense? So now that we have the energy, now we can calculate the frequency. Since the question is asking us to find the speed of the electron and the frequency, we use the same equation. We use the same equation as before, but instead of having it c over lambda, we're replacing back with v because they're the same. Because v is which is the italicized v, italicized v. So we know that h is a constant, and we know the italicized v is equal to is equal to the Planck's constant divided by the energy, and this is where we get this value, which is 1.447 times 10 to the negative 17, 1 over seconds. Now that we have the frequency, we can use that frequency to calculate the wavelength, which is the first equation that was given. So we just plug in the values of c is equal to 3, c is equal to the speed of light divided by the frequency, and we get 4.342 times 10 to the 9 meters. Because remember that c was in meters, not nanometers. Not c is in meters, so lambda has to have units of meters just for this problem specifically. So now we can calculate our velocity. So we know that the velocity is, so we know that lambda itself is equal to Planck's constant divided by the mass times velocity. So in order to calculate the velocity, we just have to bring it to the other side and keep everything else on that. I think I made a mistake somewhere. I might have made a mistake. Is h, hold on, I think I might have made a typo. Let's see right here. It was h is equal to, wait, lambda is equal to h over m star v, the v on the other side. Yeah, I didn't make a mistake. Hold on, give me one moment. So this should be down here. One should be down here. This one should stay up there. And it's, let's see here, velocity lambda down there. Okay. So it should look like, sorry. Those typos are everywhere. Look like this in parentheses, so that way. And there, cool, perfect. All right, let's go back into it. All right, so sorry for the typo. So we know that lambda is equal to Planck's constant divided by mass times velocity, which is your momentum. And we know momentum is equal to mass times velocity. I know repetitive. So what we just do is, like, we had to isolate v, and we already did that right here. We know that h is a constant. Why isn't it weird? We know that h is a constant. We know that the mass is in kilograms and lambda is in meters. So we can plug everything back in, and we can cancel out everything. Do note, and we have our velocity is equal to 5.97 times 10 negative 6 meters per second. The reason why I put the green in the S is because that's where your unit of seconds comes from, if that makes sense. But yeah, that should be everything. Yeah, that should be everything. Everything? That should be everything. All right, cool. And also, do you know this conversion over here? So know that 1 joule is equal to 1 kilogram times meters squared divided by seconds squared. That's how you get your other units of seconds. But yeah. Quantum numbers. So, mind helping me out explain this, Claire?
Oh, yeah. So there are 4 different types of quantum numbers. We have N, L, ML, and MS. So for the exam, you should know what each of these numbers mean and how to find them. N is the principal quantum number, and this tells us the size of an atom. Basically, the larger N is, the larger the size of the atom is. L is the angular momentum quantum number, and this tells us the shape of the orbital. So you learned in lecture that orbitals can come in 4 different general shapes. S is like a circular shape. P is kind of like, I don't know how to describe it. It's kind of like
the dumbbell?
like a peanut, kind of.
Oh,
yeah,
it is a peanut.
like a dumbbell.
I like it. or probably like an hourglass or something like that.
Yeah. And then you should also know what D and F orbitals look like. And for L, the numbers can be 0, 1, 2, or 3, depending on what the shape of the orbital is. So if the atom is an s orbital, then its L number is going to be 0, and so on and so forth.
Yeah.
Next, we have Ml, which is the magnetic quantum number, and this tells us what the orientation of the orbital is. So in lecture, we learned that these orbitals can be arranged in different ways. So for example, p orbitals, you can have 3 different orientations or 3 different styles that the p orbital can look like. And the numbers that we use to represent these are different for each orbital. For s orbitals, it can only be in one orientation, and when we call that orientation 0. P orbitals, they can be in 3 different orientations. So, and we use the -1, 0, or +1, depending on which subshell the electron is located in. Excuse me.
You're excused.
For d orbitals, they can have, looks like 5 different orientations. So -2, -1, 0, +1, or +2, depending on where that electron is located on the subshell. And for f orbitals, we can have 7 different orientations. So -3, -2, -1, 0, +1, +2, or +3, depending on where that last electron is located on the subshell. And finally, we have the ms number, which is the electronic spin quantum number. This tells us which direction the electron is spinning. Electrons can spin in 2 directions, upwards or downwards, and we use 2 numbers to represent this. We can use a -1/2 to represent the electron pointing down, or if it's pointing up, we use +1/2 to represent this.
And you always look at the sorry. Right. And for the spin, you always look at the last electron you fill out in your orbital diagram. Let me see here. So yeah. Okay. So let's try an example of a full electron configuration, an abbreviated configuration, and Nlx configuration for oxygen. So here we know that going to your periodic table, we read the electron configuration. So we go from left to right down. So we go from left to right. So it's 1s, 2, 2s2, 2p4, and 2p4 should be the location of oxygen in your periodic table. So that's the full electron configuration. All right. So here's the periodic table. So we have n is equal to 1, 2, 3, 4, 5, 6, 7. So we go 1s, 2, 2s, 2, 2p4, and there's oxygen right there. Now the abbreviated electron configuration, we always go with with the noble. We just basically replace it with the noble gas. So instead of writing out like 10 to 15 different like 2s2s, 4d10s, and all that other stuff, we can use the noble gas as a shortcut, because we know that noble gases are practically, stable molecules. So all the electrons inside the noble gas are pretty much not going anywhere. So we always write the noble gas in brackets. Make sure you put it in brackets, because if it's in parentheses, that would be incorrect. So for the notation, so it's bracket helium. Back. So we know that helium is a noble gas over here. So we keep it of helium, and then it's 2s2 and then 2p4. So yeah. Now that the Nlx configuration is just basically the last piece of your electron configuration. I don't think Sharuzel went over this with you, but it's a good way to get a little bit more practice. It's kind of like a helpful tip. So you have your abbreviated right here. You only look at the last piece you filled in, which is 2p4, and that's your Nlx configuration. Cool. So now then, with using the Nlx, we can actually use it to find the quantum numbers for oxygen. So 4 quantum numbers for any elements are by looking at the last electron in the last orbital of the element. So anytime you have your electron configuration, the last thing that you fill out is what you use for your quantum numbers. So like example, back over here in oxygen, 2p4 was the last thing that you filled out with electrons. So that's the one that we're going to use for your quantum numbers. So you have N, your L, your ML, and your MS. So we know that the first number in front of the, which is this 2 right here, is your N, your principal quantum number. We know that L is your, N minus 1 is going to be your L value, which is, but remember that L can either be 0 or 1 because it's still lower than, because it still applies to N minus 1. But how we find out if it's either an S or P orbital just by looking at, the P itself. Because we know that in an S orbital, L is equal to 0. But in a p orbital, L is equal to 1. In this case, we do have L is equal to 1, which is this p orbital right here. So that's our second quantum number. The third one is basically doing where the last electron is located. So if we do this, we go -1, 0, +1. We always fill everything out first, and then we go back. Then we go back to fill in the last one. So the one here in this that's circled is your ML quantum number, which is -1. And of course, the spin is the direction in which the electron is going. And since it's the last electron has a down arrow, it has a spin of -1/2. All right. Oh.
Wait, I have a question.
Oh yeah. What's up?
How do you know how many electrons are there?
You know how many electrons are there? So how to know how many electrons are there for your whatchamacallit?
Or in like the last orbital right here?
Yeah.
Because you have to draw in the arrows.
Yeah.
Here we drew 4 arrows. Like, how do we know?
Oh, you look at the if I can find it. You look at, so over here we see the 2p4. This 4 up here is how many electrons you have to fill in.
Okay.
And we know that, yeah.
It'll be given to you. Or you have to count it.
Yeah, assuming you did the electron configuration correctly, and also, yeah, but it will be pretty much given to you. So you look at this 4 up here, you look at the number that's up here in your last keyword, last piece of your electron configuration. So it always has to be the last thing that you look into. If that makes sense. Hopefully it does. So, okay. So now let's go on to periodic trends. So as you know from before, you know all this information about your periodic table of elements. You know that 1A is alkali metals, 2A is alkaline earth metals, the big huge portion of middle is transition. They +3, +4, -3, -2, -1 is your halogens, and the noble gases are 0. You do note that the amount of electrons and protons is equal to the atomic number, and you have the atomic mass down there. You have the element symbol, and you already have the name, which is this information right here. So up to this point, you have that much information about the periodic table. Now let's take it up a notch by giving a periodic trend. So back in class that as you increase your energy level, your atomic radius increases. So if you go all the way down to where Fr is, which is francium, shout out to France, francium. Francium is the one that has the largest atomic radius, because since we're going down all the way to the left, and we went down as many energy levels, which is up to 7, I believe, in this periodic table. 7. We get down. we know that right here, like these elements over here are the ones with the largest atomic mass. And I believe the concept for that wasn't the concept for with cations and anions the same thing too.
I'm not sure.
All right. You might have to ask y'all might have to ask Dr. Kelly about the cations and anions if that trend still follows through. I'm not 100%. We're not 100% sure on that. But yeah, that's the trend for increasing radiuses. So if you know that this is increasing radiuses, let me ask you, Claire, what would fluorine have? Would fluorine, this F over here, have a very large radius, or it had the smallest radius?
It would definitely have a small radius because it's in the opposite direction of the trend for increasing radius.
Yep. So everything over here has very, very small radii, which is the plural of it, or radiuses. I don't know. But moving on. So yeah, that's pretty much the thing behind it. It does get kind of confusing when they ask you about like example. Let's look over here: phosphorus, silicon, germanium, and arsenic. It gets kind of confusing when they ask you like what is the how do I say these?
The largest radius.
Thank you, large radius. Yeah, let's get kind of like kind of wonky with that one. But as long as you like follow the trend of like going down to this little corner over here, I think it should be fine.
I think a good strategy for these four, for example, is you always want to look by row first. So whoever is on a lower row will have a larger radius. So we can cross out like silicon and phosphorus, for example, because they're sitting on a higher row. So we can focus on germanium and arsenic. Once you figured out who's sitting on the lower row, you can look at who's closer on the left-hand side to this corner right here. So since germanium is sitting on the left side, which is closer to francium, germanium will have the biggest radius out of these four elements right here. So that's just like a helpful way to understand the trend. You look by row first, and then you look by left or right for who's closer.
Yep. All right. So I believe on Monday you'll be learning these next periodic trends, but we're just gonna like drop it in right here, right now. So the first one is increasing ionization energy. So what increasing ionization energy mean is that the energy it takes for an element to become an ion. So which one of these is most likely to become an ion? So if instead of going all the way to FR down here, elements in the upper right-hand corner are more likely to become ions. You'll go into more detail on this probably on like Monday or something like that, hopefully. If not, then it's a good food for thought right here. So instead of going to what's this, right to left down, we're now going from left to right up. So elements all the way in the upper right-hand corner all have like the ability to become more likely to become ions, which makes sense. So, and speaking of which, all the other trends are pretty much the same. So we have increasing electronegativity. So basically how negative an electron can be. So oxygen and fluorine up there, they are the most negative people to be around. That's what, so you don't want to like, so they're the most negative elements there are because they just want to keep on absorbing electrons and stuff like that, which is the reason why that it's and electron affinity, basically how electrons are to electron affinity again. Let me double check. Give me one moment, please. I got to make sure that I'm saying this correctly. All right, so electron affinity, chemistry, the electron affinity is an atom is defined as the amount of energy. It's basically how much energy is the amount of energy for it to be the amount of energy for an element to release to become negative. So again, which one of these would be the one to become more negative? I get, in a sense. Well, of course, that would be
I
fluorine.
think electron affinity is like how badly that element wants to gain electrons. Because if you have an affinity for electrons, it means that you really, really like it. Like if I have an affinity for like skateboarding, it means I'm really into skateboarding.
And for
So
me,
I think,
and then
yeah.
for me, who has an affinity for like anime girls, I guess.
Oh my god.
That's
So if you
shoot,
think
that's
about,
recorded. Oh, whoops. All right, so
if you
yeah.
think about chlorine, in NaCl, for example, chlorine is always the negatively charged ion because chlorine has a really, really strong affinity to keep an electron. And when you keep an electron, you become more negatively charged. So that's like a really good way to better understand electron affinities.
Yep. And I believe that's all the slides we have.
Oh my
Oh,
god.
wow. Wow. We have like,
Okay.
hold on, we have like 9-10 minutes left or something like that. Wow. Can't believe it. All right. So,
I'm gonna stop recording here.
yep. And thank you everyone for watching it. Hold on. Thank you everyone for watching the session.
We'll have
And
like 8 minutes for like Q&A.
all right,
Oh,
let's
and
do
remember to sign in on
sign
the
in.
sheet.
You sign in. Tell me about the halogens in the periodic